Welcome to the beginning of our study of triangles. We'll start with general properties of triangles in this submodule. In the next submodule, we'll focus on special properties of right triangles. Triangles are polygons with three sides. Triangles can be classified based on the structure of their sides. In the following way. The nicest type of triangle is one in which all three of the sides have the same length. We call these equilateral triangles. Equi meaning equal, lateral meaning side. The next nicest case is if two of the sides are the same, but one of them is different from the other two. We call this an isosceles triangle. And if all three sides are different, this is somehow the most generic and difficult case to deal with. We call this a scalene triangle. And we also give a special name to a triangle in which one of the angles is a right angle. We call this a right triangle. So let's look at some pictures. For an equilateral triangle, the picture is perhaps something like this, where all the side lengths are the same. Equilateral triangles have an additional benefit that all of the angles are the same. So same side length, same angles. Isosceles triangles have two sides that are the same, but one that's potentially different. These also have special structure for the angles. The angles that are opposite the sides that have the same length are the same. So this angle here is the same as this angle here, but this one is potentially different. So it's nice to know that in addition to having two of the same sides, it has two of the same angles. And then scalene are the worst. These are ones that have all the sides different. So maybe something like that, where this is different from this is different from this. And all the angles are also different. Great, so we've introduced these notions for triangle. Let's look now at formulas for area. So the perimeter of a triangle is the sum of its side lengths. and the area is the two-dimensional space it encloses. Perimeter is simple to compute. Just add up the three side lengths. Area is a little bit trickier. We have to use a formula. The area of a triangle is equal to 1/2 its base length times its height. So similar to a square, we'll see, except I have to divide by 2. So let's look at a few examples. So let's say I have a triangle with base length 7 and height equal to 4. Then the area of this triangle is 1/2 base times height. So 1/2 7 times 4, which is 14. Pretty straightforward. Let's do another. We'll look at a right triangle. So here, let's say that the height is 8 and the base is 3. Then the area is equal to 1/2 times base height. So 1/2 times 3 times 8, which is 12. Pretty straightforward, I think. The only thing you have to really be careful about is making sure that the height that you find is actually the height of the triangle. Keep in mind that the height here was this vertical distance. It was not equal to one of the sides. It was a separate quantity. So let's now talk about angles. So an important thing to keep in mind about triangle angles is the angles must sum up to 180 degrees. So if I take the three angles in any triangle and add them up, it's always equal to 180. As a nice corollary to this, each angle in an equilateral triangle must be equal to 180 divided by 3, since they're all the same, so 60 degrees. And we give a special name to any line which splits an angle into two pieces. We call that an angular bisector. So let's look at some examples regarding angles. Let's start with a triangle that's missing one angle. So this angle is unknown, and we'll write theta. This is the common notation, 105 degrees. Let's call this 40 degrees. We would like to solve for the missing angle size. How do I do this? Well, I know that all three of the angles must sum up to 180. So I know 180 is equal to theta, the unknown, plus 105 plus 40. So 180 is equal to theta plus 145. And now I just solve this algebra problem. So theta is equal to 35. Not too tricky. Sometimes you might be asked to solve problems like this that exploit additional structure in the angle. You might be asked to solve a problem involving isosceles triangles, like the following. Suppose that I knew that this was 30 degrees, and that these side lengths were equal at 5. And I wish to solve for this angle theta. I cannot proceed directly as I did in this example because I'm only given one of the missing angles, not two. But I can use the fact that this is an isosceles triangle. So this angle, theta, is equal to this angle here. These are necessarily equal. So I can solve as follows. 180 is equal to 30 plus theta, which tells me that 150 is equal to 2 theta, so theta is equal to 75 degrees. So we can use this isosceles triangle trick. As the last example, we'll combine this trick with something even more complicated, which is the following picture. So now I have an isosceles triangle, but what I'm interested in is this angle theta here. How can I solve for this? Well, I can start by finding these angles here and noting that this angle plus theta is equal to 180 since they split a line. So I'll call this x. So I can proceed as follows. I know that 50 plus x is equal to 180, which tells me after a bit of algebra that x is equal to, 2x is equal to 130. So x is equal to 65. And then I know theta plus x is equal to 180. So now I say that theta plus x is equal to 180, which implies that theta is equal to 180 minus 65, so 115 degrees. So this is an exercise here that requires us to understand isosceles triangles and also the fact that theta plus x must be 180 here, since this line splits the line that has angle 180 degrees.